You're watching a speedrun of Super Mario Bros. For the NES. The goal? Get to the end of the game as soon as possible. For this level, that means we drop down, jump over these, go through here, and then... oh, why are we in a wall? In quantum mechanics, there exists a phenomenon known as quantum tunneling. In this phenomenon, there exists a chance that a particle passes through a barrier that it, by all means, should not be able to. Now let's go back to Mario. Here, we see a kinda similar situation as quantum tunneling. Mario should not be able to pass through this wall. So how does he? Well, the game only checks Mario's position every frame, which is once every 1/60th of a second. In that frame, Mario can move either 2 or 3 pixels. Look at that! Mario's position is a wave. In one frame, he can either be here, or 1 pixel further. Now, if we have Quantum Mario, and he runs into a wall, there exists a chance that some of his hitbox, or his body, exists inside of that wall. Now the game knows that Mario is not supposed to be inside that wall, so it tries to push him out. However, if we do some specific inputs, kinda trick the game instead ends up pushing Mario to the other side. Mario has tunneled through the wall. Now let's turn Mario into a real-world object. If a particle has a certain energy E and encounters a potential barrier of height U0, if that E is greater than U0, it can go over, obviously. But what happens if it's smaller? Well, yeah, it hits the wall. But what if it didn't? The physicist Louis de Broglie proved the existence of a principle called wave-particle duality. Essentially what this principle says is that all matter exhibits both wave-like and particle-like properties. So yes, you're a wave, I'm a wave, moving your hand side to side is a wave. Now usually that doesn't matter. The wavelength of objects, known as the de Broglie wavelength, is so minuscule that it doesn't really matter much to you and me. But on a micro scale, to something like, say, an electron, that wavelength is much more significant. If we take this principle and instead put a wave into the same situation we described earlier, we see something odd. If the barrier is thin enough, there becomes a non-zero chance that the particle appears on the other side of that barrier. Like Mario, the particle has clipped through the wall. Now why does this happen? Well, instead of instantly stopping when it hits the wall, the wave function instead decays rapidly. Its decay is given by the equation e to the negative kt. If we graph that, we can see that it drops off quickly, but not instantly. So, if the barrier we need to cross is thin enough, the wave function will not decay all the way, and will leave a portion on the other side. Therefore, we have a non-zero probability of finding the particle there. So now you know why it happens, but how can we tell when it's going to happen? Remember, we're in the realm of quantum physics, so nothing is definite. But we can tell what the probability of a particle tunneling is. There's a few different ways to find this, but typically we can just use the Gamow approximation. This approximation states that t equals e to the negative 2ka, where k equals the square root of 2m times v0 minus e over the Planck constant squared. That's a lot of funny numbers. Now, what do they mean? Well, t is our big number here. It gives our transmission probability, which is what we're working towards. M is the mass of the particle, v0 is the height of the potential barrier, E is the energy of the incoming particle, and that h with the little cross on it is Planck's constant, and A is the width of the barrier. If we make the barrier wider, our t gets smaller. If we make the barrier narrower, t gets bigger. If we make it taller, transmission probability goes down, but if we make it shorter, the probability goes up. If the particle's energy is closer to that height, tunnel probability also goes up. Finally, if our particle is very light, it's more likely to tunnel. Quick quiz. If we have two potential barriers, barrier A is short and wide, and barrier B is tall and narrow, which one is a particle more likely to tunnel through? Now, this is a bit of a tricky question. As you may have noticed, each barrier has an aspect that helps and harms its transmission probability. Barrier A is short, which is good for tunneling, but is also wide, which is bad for tunneling. And barrier B is tall, which is bad for tunneling, but is also thin, which is good for tunneling. At a glance, it may seem like each barrier is equally likely to allow tunneling, but in fact, barrier B is actually more likely to allow tunneling. Well, why is that? The short answer? Width matters more than height. If we take a close look at the equation, we can see that height does have an effect on the tunneling probability. However, we also see that E gets subtracted from it and it's inside of a square root. On the other hand, the width of the barrier sits out here and multiplies the entire exponent, resulting in a larger change. At this point, I bet you're wondering, why does this even matter? Well, it turns out the answer to that question is more than you think. The sun burns because of nuclear fusion. One part of nuclear fusion is getting two protons to form a bond. One small problem. Protons are both positively charged, and like charges repel. With quantum tunneling, however, protons can convince themselves they've been close enough to bond all along. Another thing quantum tunneling affects is circuitry. Very, very small circuitry. See, because quantum tunneling exists, we have to make sure that the barriers between different sections are at least a certain distance apart. Otherwise, electrons will be too likely to tunnel through and mess everything up. So, yeah, it is pretty important. And honestly, even if it wasn't, I just think it's pretty neat. Thanks for watching. All of the information I got was from these sources. I'll also throw a link down below in case you're interested. Have a good one.